Jie, and now I'll be present about the simulation waveform analysis of our mini project. Firstly, for the equation we get is y equal to AB bar plus C plus D with a long bar at the above. And here shows the circuit we designed. In this schematic, we only use two inverters, which is at input A and input B. We designed this based on the lecture we learned. From the lecture, we know that in PMOS, the N will be in parallel while all will be in series. At above here, for the NMOS part, N will be in series while all will be in parallel. Next, the truth table. By referring to the equation, this is the truth table we get. The Y output will be high at 0, 1, 0, 0, 1, 0, 0, 0, and lastly 1, 1, 0, 0. Next, for the output waveform, after doing the test bench, this is the waveform we get. To verify it, we compare it with the truth table we created. After comparing, we verify that the output waveform is similar with the expected truth table itself. For example, at 0, 1, 0, 0, it will be high, and 1, 0, 0, 0 also will be high. Thank you.
Hi, my name is Muhammad Alif Amshah bin Muhammad Azahar. So for my part, I will present about the layout design. First, for the transistor level and the Euler path. From the equation, the A and B inputs have bars. So for these inputs, we need inverters to convert A to A bar, B to B bar. So as you can see in the diagram, we use about 12 transistors here. So for the Euler path on the PMOS, it starts from the drain of the A bar and flows to the source of A bar, which connect to the VDD, and same goes to the source of B bar. So it flows to the source of B bar, then to the drain, and then flows back to the source of C, drain of C, and to the source of D, and goes to the drain of D input. So it's a little bit different here on the NMOS, which the source of B bar, C and D is connected to the ground. The Euler path consequence is the same, which flows from A bar to B bar, C and D. So for the stick diagram, on the left side, there are two inverters there, which two inverts from A to A bar, B to B bar. So the outputs from the inverters here will connect to the poly of the inputs there. So as you can see, there is the pink lining there, which represent of metal 2. So why we use metal 2 here? This is because we want to prevent from the metal 1 is overlapping. So instead of using metal 1, we use metal 2 to prevent overlapping. So this is the layout imitation from the stick diagram. This is the final layout. So it is different from the stick diagram as we compact the size. So we combine the inverters here to reduce the size of the layout. So let's take a look at the drain of input A that connect to the drain of input B on the PMOS. So from the stick diagram, we use metal one material, but in here we use metal 2. This is because we found an error on the LVS. So if you use metal one here, it will overlap with the other metal one there. So that is why we use metal 2 to prevent the overlapping. So that's all for my part.
Okay. Assalamualaikum and hi. My name is Muhammad Amir Faris bin Muhammad Rizwan. So I will presenting for my part that is analysis of the layout design. So okay, this is our final layout without any error. Before we got this result, we have about 12 error for the RC, then 3 error for LVS. It quite hard to achieve this result. So to prove that we succeed in getting this result, so I include our DRC and LVS verification success. Uh, as we can see here, there is a green signal here with smiley face, so that means we achieve our objective to get a no error verification for layout. So for DRC analysis, as I said earlier that we have 12 errors, so I take 3 error to show and how I solve it. So for the first error here, it said active line are too close with metal 1 connection. The gap measurement must be minimum 1.5 lambda. So as we can see here, there is a white line here that been bold here. So the error here is because that contact to active here is too close with the active line at the top here. So how I solve it, I just move it a little bit to the center so that this contact to active layer have a gap minimum 1.5 lambda. If is bigger, there is no issue, but it cannot be too small. Okay, next for the second error. For the second error, the width of polygate are too small. It must be minimum 2 lambda width. So here we can see there is a bold white line here, so that means that our polygate here is too small. Doesn't It was smaller than 2 lambda. So to solve it, I just use a ruler and put it here to make sure that my polygate is actually 2 lambda. It can be more than 2 lambda, but it cannot be less than 2 lambda. Then for the third error, there are no metal 1 layer cover contact to active layer port for connection. There is 4 error here that I got. That is because I mistakenly no no I forgot to put another layer here because for port for connection it must contact to active must be covered by metal 1 layer, so it can be a perfect port connection. So that's all for the RC. Then for LVS error, I said that we have 3 error, and that 3 error are the same error where the connection between metal 1 and metal 2 there are no via. In our layout we use metal 2. That is because we want to avoid any overlap connection. So we use metal 2 and metal 1, but for via, the function of via is to connect the metal 2 layer and metal 1. If there is via, so the connection will be good. If there is no via, so there is no connection between these two layers. That's all from me. Thank you.